Now we've just done ionic formulas, or formulae, and so we're going to talk about covalent molecular formulae now as well. So the procedure for developing these formulae is the same as for the ionic case. The way we do it is very similar. The only difference is that you don't need to worry so much about the charge, and we'll go through that as we go. The more difficult aspect of this naming convention and writing covalent formulae is naming the compounds correctly. Okay, so so the process is exactly the same. You make an electrically neutral compound, but the difficulty becomes actually naming the compound. So there we have our issue. So naming covalent molecular compounds is what we're going to focus on. So just remember the process is exactly the same as the ionic process. So you use the normal element name for the leftmost element on the periodic table. So if we were to deal with, say, why don't we go with carbon dioxide, okay, CO2. We know that's a covalent molecular compound. So you can see carbon is here and oxygen is here. And you can see carbon is further to the left than oxygen. So we just use its name as the first part of our compound name. So we have carbon here. So the leftmost, you use the normal element name for the leftmost element on the periodic table, and an "-ide" suffix for the other element. So the other element is oxygen, but instead of writing oxygen, we drop the "-igen" part and we give it an "-ide" suffix. So it becomes oxide, right? And because there's two, we write di meaning two. You can see that that's our carbon dioxide, which we're all very familiar with. So that's an example of how we name covalent compounds. Now, the question then becomes, oh, well, what happens if you've got oxygen and sulfur together in, say, sulfur dioxide? Which one do we put first? Well, the one you put first is the one lower down in the group. So you can see sulfur is here and oxygen is here. So sulfur is below oxygen, so it comes first. So it becomes sulfur. And then obviously the "-ide" stuff comes up after, oxide. And there's two, so it's di, sulfur dioxide. And so if they're in the same group, it's the one that starts is the one lower down in the group. Now, an exception to the rules is that oxygen is named last in compounds with Cl, Br, or I in them. So for instance, Cl2O shouldn't be oxygen chloride or oxygen dichloride. It's actually always oxide is last. Okay, so pretty much in all cases, yeah, oxygen will be last. So oxygen is always the last chemical you write. So this one is actually chlorine monoxide, not oxygen dichloride. So this one here. Even though chlorine is further to the right than oxygen, this exception sort of gives you a little bit of leeway there. Now the number of atoms of each type is given by using the prefix mono, di, tri, tetra, penta, or pent, depending on the situation. Hexa, hepta, octa, and all those other you know all the rest, surely, in front of each part of the name. So carbon dioxide, there were 2 oxygens for every 1 carbon. So we use di as the prefix, so it's carbon dioxide. Okay. Now if it was, for instance, SO3, we would use sulfur. 3 is tri, so sulfur trioxide. Okay, so that's just how we name different chemicals. So that concludes today's lesson on the basics of chemical formulae. We've looked at ionic chemical formulae and covalent chemical formulae and how we develop them, how we figure out what is the actual chemical formulae or formula for that particular compound, and how we name it as well. Okay, so hopefully in the question segment we'll get more practice at doing these, or at least learning how to do these, and you'll hopefully learn on your own how to get these equations or formulae and how to write the chemical names. Okay.